All right, let's do it. Standard model. Standard model is the most up-to-date model we have today of the universe around us. So it's the combination of a bunch of different particles and how they interact together and how they form forces and how those forces interact together. If you've been watching the news recently, you've learned a little bit about the Higgs boson without even knowing about it. Have you ever heard of gravitational waves? Well, the Higgs boson is the particle that is used to describe how gravitational waves propagate. But we're not going to go over too much about the interactions between them. Let's take a step back and let's look at some more fundamental things. Let's look at the four fundamental forces that we know about. So there's four fundamental forces and interactions with the weak force, the strong force, the electromagnetic force, and gravity. Okay? The standard model is able to describe the interactions really well between the weak, the strong, and the electromagnetic. But it's important to note that gravity is not supported by the standard model. But we know gravity exists, so there must be some model that we can use to also understand gravity. We'll get to that. But it's important to know that only the strong, the weak, and the electromagnetic forces are explained through the standard model. Okay? And these are consistent with relativity and quantum physics, which makes us science and physics nerds out there really, really happy. But we still have a little bit more to learn. First force that I mentioned that we're going to go over is the gravitational force. We know once there's two masses, any two masses of any size over any infinite distance, they'll have a gravitational force. Okay? It's the weakest of the fundamental forces, but it expands over an infinite range. Second force is the electromagnetic force. Again, an infinite range, but it's the attraction between two charged particles, or the repulsion of two charged particles. Remember, like charges repel and opposites attract. Okay? And it's responsible for how matter gets its shape. So it's pretty important. Next, we got the strong force. Okay? The strong force is responsible for holding the nucleus in place. Okay? It's got a finite range, pretty small, 10 to the negative 15 meters. So it's only really as big as about an atom, right around that size. Okay? And it's so strong, that's why they call it a strong force. It's so strong that if you're able to break the strong force, an immense amount of energy is released. And that is called a fission reaction. Okay? That's how we get energy from a fission reactor. We break apart the nucleus into individual components, and energy is released. The final force we have is the weak force. Okay? The weak force is still important. It's responsible for radioactive beta decay, and this is when a neutron, so we have n to the 0, meaning it's got no net charge. A neutron breaks apart into a proton, an electron, and what we're going to call an electron antineutrino. Okay? Don't get scared by this. We'll go over it a little bit. Okay? But, question. If I look at the reference table, and I go to the very front page, why does it tell me that the mass of a proton and the mass of a neutron are the same at 1.67 times 10 to the negative 27 kilograms? When right here I'm looking and I see the neutron must be composed also of electron and an electron antineutrino. It means that the neutron is actually slightly greater in mass than the proton. So that's important. That's a question that you'll see on the regents. A neutron has a larger mass than a proton, only by a little bit, but the neutron has a larger mass than the proton. Again, the same as the strong, it has a finite range. This is actually smaller than the range of the strong force. And just to break down, so that way you get a sense of what the relative strengths are. If we said the gravitational strength is 1, the weak force would be 25 times greater than the gravitational. The electromagnetic force would be 36 times greater than the gravitational. And the strong force, the strongest of the forces, see, makes sense why they call it the strong force. The strong force is 38 times greater than the gravitational force. Well, we spoke about the standard model before, and that tried to understand and combine together all the different forces we have and all the different ways we have of thinking about the universe. So one theory combined the electromagnetic force and the weak force, and we call that the electroweak force. Then we took this electroweak force and we combined it with the strong force, and we got the grand unification theory. Taking it a step further, if we're able to find a model or a theory that combines all 4 fundamental forces, we're going to call that the theory of everything. Pretty mind-blowing. If you're able to find that, give me some credit. But this is the overall goal of physics, the overall goal of understanding everything around us. That's why we study physics, to understand everything around us. Okay. If we took a neutron and a proton, we used to define those as indivisible particles. Well, when we looked even further, we started to understand that they're made of what's called quarks. If we open our reference table, we see that there's a whole list of quarks here. We have up, charm, top, down, strange, and bottom. So if you're unsure about the names, don't worry. They are available in your reference table. It's fine. I was going to zoom in. I can't figure it out. Okay. Matter that we know of, matter is made up of, well, matter and what's called antimatter. Okay? Antimatter is nothing really different than regular matter. It's the same exact mass, but it has an opposite charge. So if I had a proton has a charge of 1 elementary charge. And we know it's positive, so I put the plus there. If I had an antiproton, and we denote anti by just a bar at the top, this has a charge of -1 electron. Okay? So antiparticles are depicted with the bar over the symbol. And here's our quarks again. So quarks have 2 options. They can either have up, charm, and top, which all have a charge of +3, +2/3. And then we have down, strange, and bottom, which all have a charge of -1/3. So the combination of any of these, the combination of 3 of these, will produce a charge that's maybe +1, maybe -1, maybe 0, and we'll see those combinations in a bit. Taking it a step further, particles can be broken into 2 groups, which we also see here. So here's our matter and our particles, and we can break them into leptons and hadrons. Well, what's the difference between those 2? Leptons, which we saw over here, leptons can either have a charge of 0 or -1. They do not experience the strong force. So if they don't experience the strong force, then they're not in the nucleus. So examples of leptons would be an electron, a muon, a tau, and a couple others. As well, they're antiparticles. So the antiparticle of an electron would be an anti-electron, also known as a positron. Muon would be a positive muon, not really creative. A tau would be a positive tau. And the leptons, like we see over here, are located right here in the bottom right of page 3 of the reference table. So when it comes to quantum physics, or modern physics in general, a lot of it is available right here on the reference table for you. Okay? As well, it even notes in the bottom, underneath the chart of the particles of a standard model, it notes that antiparticles have an opposite charge as regular particles. So if you forget that, it's available in the reference table. Okay, the other side of matter, so we had leptons, now we have hadrons. Hadrons can be broken apart into quarks. And each hadron has either 3 quarks or 2 quarks. So we break those apart into baryons and mesons. Okay? As well, I'll take a step back, the hadrons experience a strong force. Since they experience a strong force, they're located in the nucleus. So what other particles do we know that are located in the nucleus? Well, we got protons, and we got neutrons. So both of those are made up of quarks. So a baryon has 3 quarks, or 3 antiquarks, and a meson has 1 quark plus an antiquark. So these are all examples. Don't freak out. A lot of them are available in our reference table that we can look up. So don't freak out about memorizing these. You don't have to. What I want to do now is just get a little bit of practice in. Okay, try this one out. So we have a down, strange quark composition. And what would be the classification? Remember, there's 3 quarks. What is a classification of 3 quarks? Okay, so we have down, which has a -1/3, a down, which is a -1/3, and a strange, which would be -1/3. We've got 3 -1/3, so we're going to have -1e. So our charge would be -1 elementary charges. Try this one out. This time we have a strange plus, what would this be? This is a U with a little bar across the top. This would be an anti-up. Recall, anti means opposite charge. So if we have a strange that has a charge of -1/3, and we have an up, normally ups have +2/3, but since it's an anti, that'll be -2/3. So -1/3 plus -2/3 gives us a -1 electron, elementary charge. And that would be classified as a meson because it has 1 antiparticle and 1 regular particle. What charges are allowable for a meson? So play around and try to figure out what are the possible charges for a meson. Remember, you can only have a quark and an antiquark. Okay? So the correct answer was -1, 0, and +1. Okay, play around with this. I want you to give me 3 examples of quark combinations that make neutral baryons. Recall, a baryon means that it has 3 quarks. So what combination of 3 quarks will give you a neutral charge? So here's 3 examples. We have an up, down, down, charm, strange, strange, and top, bottom, bottom. So notice, up would have +2/3, -1/3, -1/3, 0. Charm, +2/3, -1/3, -1/3, 0. Top is +2/3, -1/3, -1/3, 0. Okay, so we're getting the rhythm. Last example. Give me an example of a quark combination that makes a baryon with a +1 charge. Okay? How do we get a +1 charge with the possible combinations that we have? Okay, there we go. So possible combinations. This time we're going to combine together two quarks that have a plus 2/3, and then one of them will have a negative 1/3. So plus 2/3 plus 2/3. Now I have 4/3, and then my down is negative 1/3. Same thing over here. Up and charm will both get me 4/3. Strange minus 1/3. So for both of these examples, I'm having plus 1, plus 1. Up and top together is going to get me 4/3, and my bottom is going to be minus 1/3. So together, I have plus 1. These are the type of questions that they're going to ask you when it comes to quarks, antiquarks, mesons, bosons, hadrons, leptons. So don't freak out about the vocabulary. Have a wonderful day, everyone.